Hey, hello students. Today's class will continue with the problem we left out of the previous class. So we are starting off with the numericals with respect to keys, right? So this is the third module. We are starting off with keys and couplings, right? Okay. So the question stated it's a rectangular key of required dimension. Dimensions were given 10, 14, and 75. Torque also was given in terms of Newton meters, and diameter given as 50 mm. This is diameter of shaft, and shear stress and crushing stress both were given. Okay, so using this data, we had to find out whether it is sufficient or not. Given crushing and shear stress were sufficient or not. So we know all dimensions. Only thing we need to establish now is whether it is sufficient or not. That's it. Okay. Not much of a big deal. And we are starting, we already started with this problem in the previous class. So the thing is, it was using this equation, that is 19.5, we had to solve. But I want to point out a small change here. So here, shear stress, this is a small mistake in the data handbook. It is tau d2. This entire thing is together. So this should be written as tau d2. Right, so this is how it should have been written here. So that's the small error which we have in the data handbook. So this is essentially 2mt divided by tau d2 L and D. So this is how it should be written, but for some reason they have forgotten the subscript. Okay, it should be written as tau d2. Okay, that's the shear stress of the diameter. That's what is that's how it's meant to be. So if you go according to this shear stress equation, so this satisfies. So 14 is the dimension, assuming the crushing, shearing stress, not crushing, shearing stress. Assuming shearing stress is how you find out. Now let me just find what is the length of this. So you just use it in the formula. So L equals, substitute everything over here. So 2 into 1200 into 10 power 3 divided by 56 into 50 into 14. So once we just solve this, we'll get the value over here. What should be the length according to the given stress values. So continuing, this is general equation which we use to find the torque. So we need this to find the length. So use that and find the torque using the MT. Okay, so using this power equation, general equation, and this table 17.1. Okay, this 17.1 table, you'll find what is the breadth and height. So this is a quick way to find out. So you see, for shaft diameters of our range will fall here. Okay, so our range will be here. This is 12, 22, between 22 and 30. So we need to choose between 8 and 7. So we'll take the maximum. Since this is a square key, let's take the maximum. Okay, let's say from table 17.1 for diameter 25 mm, I'll take B equal to H equal to 8 mm, because it's a square key. So the question clearly states that it is a square key, right? So if it was rectangular, you would take whatever is given here, 8, 7. But see here, length is not given. So since length is not given, you need to find length using the crushing stress or whatever stress value you have. The crushing stress is not given here. Right? So since crushing is not given, you need to use the shear stress value. You can use the shear stress value and find out with respect to the this thing. What do you say? And you can equate that to the crushing stress to the yield stress values using the factor of safety value. So we'll see how we can we'll find a best fit method for this. Let's see. So now that this is fixed, breadth and height are fixed. That is at the square key. Only we need to fix the length. Okay, so this we are doing to find length. So this is equation 17.1, but we'll refer to 19.1 and 19.5 and 19.51. So these two equations which we previously referred to, right? So for width of keyway and thickness of. So before that, you see crushing stress and shearing stress are not given. So what is this? B equals 2 mt divided by tau d2 L and D. So this is 19.5. Okay. Similarly, one more equation, that is H equal to 2 mt 2 or 4. Okay, let me just check this again. The data handbook. 1951. That's 2. It's 2 only. So 2 mt divided by sigma b dash L D. This is 1951. So using these two equations, we'll find the length. So and also we don't have two other values, that is crushing stress and bearing stress. So we don't have still these two values, crushing stress and the shear stress. So these two values we don't have, but we need to extract that somehow. Okay, how do we extract that? We know the yield stress, right? So bending, I'm sorry, this crushing stress is equal to sigma y yield stress by factor of 6, and just equate to this here. So this is given as 450 divided by factor of safety was 3. So just divide that and we'll get the answer. Similarly, shear stress tau d2 is the standard notation, tau d2. So this is given as 50% of yield, 0.5 sigma y by factor of safety. So this standard formula. Okay, crushing and shearing stress, standard formula what we use. This is 0.5. This is 50% of yield divided by factor of safety. So these two values will give us the extreme stresses, right? 450 over 3 is 150. This is 150 newtons per mm squared, and similarly into half. So half of that will be 75 newtons per mm squared. Okay, so now we have the extreme values of stress. So using these two, whichever length will be maximum, right? So that's what we use. B and H, substitute both of these values here and find the length. So substituting, it is 8 equals to 2 into torque. So torque, what we got is 191 into 10 power 3. 191 into 10 power 3 divided by, and it is LD. The tau is 75 into L into D. D is nothing but the diameter of shaft, that was 25 mm. So from this we get one value of length, and this is assuming the shear stress. Assuming shear stress. Similarly, assuming the crushing stress, we get one more value. This is in crushing. This also comes to 8 equal to 2 into 191 into 10 power 3 by sigma b, that is the bearing stress. Bearing stress we got 150. This is 150 into LD. L, again we are required to find L into D. D is 25. So again from this we get L. So let's see how much the length comes to using both these two equations. It's 2 into 191E3 divided by 5 into 25 into. So we got 25.46. Okay, so this is 25.46 mm, and what about here, the crushing strength? Using the crushing strength, this divided by 150 into 25 into 8. Here we get a smaller length. Okay, smaller length, that is you get 12.73 mm. Okay, so this being smaller, we'll choose the bigger one as our length, and we'll just approximate it so that it's rounded off. Let's say 26 mm somewhere. So you write the conclusion. So therefore, the dimensions of the square key is 8 into 8 into 26 mm. So that will be the dimensions of the square key. That's how you can approximate this value. Okay, move on. Next problem. Okay, so in this problem, you have a mild steel shaft. It has to transmit 100 kilowatt power at 250 RPM, assuming the shaft and key are made of same material. Design the sunk key. The allowable shear and crushing stress are 40 and 72 newtons per mm square respectively. So it's a sunk key. So sunk key in the sense it's just it can be rectangular or it can be even square or any other form, but no, mostly it means rectangular only. Okay, let's write down what is given. So data is given as power P equals okay, so power is given 100 kilowatts. 100 kilowatts. Then you have N, the RPM as 250, and you have to design this sunk key where allowable shear stress. So tau D2. The allowable shear stress. This is how it is written. Okay, in the data handbook it is D2 is written as separately, so don't get confused with that. That's a small error. So tau D2 is 40 newtons per mm square, and crushing stress sigma V dash is 72 newtons per mm square. So even at first you get these notations wrong, not to worry. Once you see the actual equations in the data handbook, no, then you just equate, relate them to these stress values. That's it. So you need to design the key, means you need to find the dimensions basically. So we are finding B, H, and L. So note here the diameter of shaft is not given. Okay, so we need to design this purely by using torque. In the torque, and we need to somehow extract the diameter of shaft also. Okay, so that's how it works. Let me copy this. So that's our problem. So required to find all three dimensions. Okay, and we can come to know only our BA and H only when we have the diameter. Right? So let's start off. The solution for this. First up, let's find the torque. So torque is power equation. The power P is given by 2 pi n T. Let's write MT. MT, that is torque, divided by 60,000. That's in kilowatts. Now let's substitute everything else. So we have power as 100 equals 2 pi into RPM. RPM was 250. Slow RPM 250 into torque MT divided by 60,000. So with this we'll get what is our torque in Newton meters. So let's see how much that is. You have 100 into 60,000 divided by 2 into pi into 250. Okay, that's coming to around 3819. Can round it up. So it's coming to 3820 Newton meter. So let's put this in order. That is, make it in mm. So MT is 3820 into 10 power 3 Newton mm. So that's our torque. Now once we have the torque, we need the diameter, because without diameter we cannot find the length. So we need three dimensions here. So in the previous equations which we used, we needed at least one of these to find the other, right? So in order to know that, we need to find what is the diameter of the shaft, okay, which in which this can take the load. So much torque is there, right? So the shaft needs to carry this. Let's find now diameter of shaft. So this again, it's given in the data handbook as an equation. So just you have these two usual equations, right? So just behind this here, 1949, 1949, 50, 51. So these three is the most frequently used equations. Okay, these equations are also there, but usually don't find it, since these don't take into account the sharing and bearing the crushing stress. We don't usually consider this. So let's take this diameter. The diameter of shaft D equal to cube root of 16 mt by nu pi shear stress tau d. Here this new value, this is called as the keyway factor. So this value nu is usually taken as the keyway factor. I'll write it for you here better. So d is cube root of 16 mt by pi, write it as it is from there, nu pi and tau d. Here's something about the shear stress, torque, pi and nu. So this nu, what will happen now? So this nu is nothing but keyway factor, called the keyway factor. Okay, so this is usually taken as 0.75. All factors are less than 1. Whichever factor you see, they're always less than 1. And you see this keyway factor, usually most of the time it is less than 1, that is 0.75. This is frequently used value 0.75. So we'll just equate that value of nu to 0.75 and find the diameter in this case. Okay, so that is d equals, we have cube root of 16 into torque 28, oh, not 28, 3820 into 10 power 3 divided by 0.75 into pi into tau. Tau, I think was given in the question. 40 is given. This is 40. Okay, so with this, we'll get what is the diameter of shaft. So what's our value d with this? You will get, and again, if you take this value of d and plug this onto the value of stress, right? The dimensions, then you will get the actual value. So let's calculate this value. So it is 16 into 3820E3 over 0.75 into 40. You do a cube root of that equation, the answer, and 805, very big diameter. 16 into 3820 divided by 5 into 40 cube root of that. You try it again. I think we are getting diameter. I'm getting diameter as 86.56 mm. Okay, just try that once again. You need to do a cube root. If you've done a square root by mistake, it's a cube root. So d is a cube root of 16 and the whole thing. Okay, just try it once again. I'm getting the answer as 86.56 mm. Okay. And now let's look at the table for extracting the dimensions of. So that table, I think 17.1. 17.1. Yes. Somewhere here. Oh yeah, this table 17, 1, and we have it here, 8. If you can see here, 85 to 110. I don't think it's quite visible. Let me just adjust that. Paste it here and rotate this 90 degrees. 90 degree towards right. Yeah, right here. So that was for B and H. We have B H, right? So here we have it. So for this diameter, from 85 to 110 mm, this is B and H. Value of B is 25 and value of H is 14. So let's copy that. So this is from table 17.1, and this also doesn't seem right, the diameter. So we'll approximate this to 88 mm. So usually preferred are even numbers and the next highest value. Let's keep it as 88 mm. From table 17.1, and for this diameter equal to 88 mm, which falls between this range in our table. So what we'll do is we'll take B as 25 mm and H as 14 mm. It's a rectangular sunk. Okay, so if you draw a 3D diagram, this will how much it comes. So this dimension being 25 and this is 14. So only thing we need to find now is the length. So we need to consider both here, both the parameters. Otherwise, we have seen from previous experience that the shear stress is the one which is the highest value, right? The shear stress value, or that was the case of square, but here we are not sure still. So do we have both? Yeah, we have both the values, so we can experiment with these two. So let's see. So using shear stress, we need to find only thing remaining is length. So using the shear stress, or the strength criteria, I can call sometimes. There is B equal to 2mt by tau d L d. This is equation 1950. So let's use this and find the value of length. So B we got is 25 equals 2 into torque. Mt was 3820 into 10 power 3. 3820 into 10 power 3 divided by tau, the shear stress value. Shear stress here given in data is 40. So it's 40 into L into D. D we took as 88 mm. So with this we'll get what is the length. And one more time to find length, whichever is a maximum, using the crushing stress. Using crushing stress, let's find out. It's H equal to 2mt by sigma P dash L, and check 1951 LD. L into D. This is 19 51. So not much difference. Only difference is the shear stress values. And instead of B you write H, instead of tau D you write sigma B dash. That's it. So let's substitute. So H is 14 equal to 2 into MT 3820 continue. So 3820 into 10 power 3 divided by sigma B dash. Sigma B dash 72. This is 72 into 72 into L into D 88 mm. Okay, so with this again we'll get one more length. So whichever is greater, we'll fix that as a dimension. So try to calculate. That's 2 into 3820 E3 divided by 40 into 88 into 25. Ah, you're right. So it is 86.81. Length according to this shear stress, not 81, is 86.81 mm. And using the crushing stress also we need to find out. So this divided by we have 72 and 88 into it will be 14. Very small difference. We got L as, yeah, you're right. So it's 86.13 mm. Okay, so small difference. We have this as a winner using the bending stress. We can just approximate this to 87 mm. Okay, we'll write the conclusion. So therefore, we can write that the dimensions are 25 into 14 into 87 mm. That's length into breadth into height. The three dimensions. Okay. So yeah, any doubts you have, can let me know. Okay, splines will start tomorrow. So this is all with the problems on keys.